Alright, so we're going to be talking about derivatives of more complicated functions. Everything we've taken the derivative so far of has been pretty straightforward, but chains are compositions of functions. So when you see something like f of g of x, we're talking about a chain. And so we need to know how to take the derivatives of complicated compositions. And so before we start talking about the chain rule, what we're going to do is we're going to do sort of a wimpy version of the chain rule. And so suppose you wanted to take the derivative, right? Suppose you wanted to take the derivative of something like sine of 2x, right? So this isn't totally complicated. Instead of x, we have 2x, so it doesn't feel that different. And so here, we're talking about something like c equals 2. And so suppose we want to take the derivative of f of cx. Well, if we write out what that means, it means this limit. And if we distribute c across x plus h, we get this limit. If we come over here to the left, the limit that I've written there, the limit as t goes to 0, f of cx plus t minus f of cx, all over t, that's the limit definition of f prime of cx. But t matches t, and here, over on the right, we have a ch and an h, and those don't match. We can make it match, however, by multiplying on the bottom by c, and also multiplying on the top by c, since we're not allowed to change it. Since it now matches, the thing inside, this part, is f prime of cx. And then the c is just the c left over. And so you can see, if you take the derivative of f of a constant times a function, it's just the derivative evaluated at the constant times the function times the constant. And as an example, let's think about what happens if you have f of x and f of 2x. Well, f of 2x happens twice as fast as x. Every time you change x a little bit, 2x changes twice as much. And so the speed at which x normally changes is twice as fast when you replace x with 2x. And remember, the derivative is like speed. And so if things are happening twice as fast, the speed should be twice as fast. And so if you look at a on the orange graph, that's f of 2 times a. Well, if you go to 2a and look on the purple graph, the f of x graph, that's also f of 2a. And so those have the same value. It's just that for the graph of f of 2x, it happened earlier. F of 2a happens at a instead of at 2a. And so the slope at a on the orange graph should be related somehow to the slope at 2a on the purple graph. And in fact, they're basically the same. The only difference is that since the f of 2x is happening twice as fast, the slope has to be twice that of the slope of f of x at 2a. And so we get the equation that the derivative of f of 2x evaluated at a, that's what this symbol means, it means plug in a, is 2 times f prime at 2a. Now, let's talk about what derivatives really are, because it's going to help us understand the chain rule even better. Well, often when we write the derivative, we can think of it as a change in y over change in x, and as we let the change in x go to 0, right, that gives us the derivative. And so, if f prime of a is approximately equal to the change in y over the change in x, then we can think of the change in y as approximately equal to the change in x times f prime of a. Think about it like a fraction. You can multiply both sides by the change in x. And what it's really saying is that the amount that y changes is approximately the change in x times the derivative at a. And the way you want to think about that is if you have a curve and then you have a tangent line, and here is f of a, then when you go a little bit to the right, which is delta x, delta y, right, here's the actual curve, delta y is approximately where you go to on the line. That this distance and this distance are approximately the same. So we can use delta y as a pretty good approximation by going on the slope of the tangent line instead. Now, suppose we took y equals to x squared, then delta y would be approximately delta x times 2x. And if you look at your graph here, we can see when we go from a to a plus delta x, we should go from a squared to a plus delta x squared. But instead of going to a plus delta x squared, we can just go to a squared plus 2a delta x. As an example, instead of squaring 3.1, here we're going to let a be 3 and delta x be 0.1, right? Then 3.1 squared is approximately equal to 3 squared plus 2 times 3 times 0.1. And that's 9.6. And if you actually square 3.1, it's 9.61. Those are actually really close. We're only off by 1/100th. That's not bad. Now, if delta y over delta x is approximately equal to dy over dx, right, those are about the same. dy dx is the derivative, it's the actual derivative, and delta y over delta x is an approximation of the derivative, then we can think of dy as the amount y moves when we move x, which is dx. So what happens when we have a chain, right? X first goes into g, and then that goes into f. Well, when x moves a little bit, that's going to make g move a little bit. But then when g of x moves a little bit, that's going to move f a little bit. And so we can think of the derivative of f of g of x as being how much f of g of x moves when we move x. Well, that's the amount g moves when we move x, compounded with the fact that when we move g, it moves f. And the way we write that gives us the chain rule that f of g of x prime is f prime of g of x times g prime of x. Now, let's do 3 examples where we actually compute some derivatives using the chain rule. In order to do the derivative using the chain rule, the first thing you have to do is figure out what is f of x and what is g of x. So write f of g of x equals the function you're trying to take the derivative of. The first thing that happens to x is always g of x. The last thing that happens is always f of x. So here the first thing that happens is 2x plus 3, and that's my g of x, and the last thing that happens is squaring, and so f of x is x squared. Take the derivatives of f and g, so we can plug them into this nice formula. By plugging them in, we get that f prime is 2 times whatever's inside, so f prime of g of x is 2 times g of x times g prime of x. And if we go ahead and plug everything in, we get 2 times 2x plus 3 times 2, which is 4 times 2x plus 3, which is 8x plus 12. How about the derivative of sine of e to the x? Again, we have to identify f and g. G is the first thing that happens to x, which is x is being put into the exponential e to the x, and f is the last thing, which is sine of. So f is sine of x, and g is e to the x. Let's write the derivatives, that way we can plug them into this formula, and we get cosine of g of x times g prime of x, which is cosine of e to the x, times e to the x. If we switch e to the x and sine of x, we could take the derivative of e to the sine of x. Well, again, write out f of g of x and try to figure out which is f and which is g. G is the first thing, so g is sine of x, and f is the last thing, so f is e to the x. There we go. Write out the derivatives, plug them into this formula, and what we get is the derivative is e to the sine of x times cosine x. So, go ahead, practice using the chain rule. Remember, the most important thing is identifying which is f and which is g, and being able to use the formula. Do the homework, come back and see the next video, and I'll see you next time.